Let me thank you for giving me very nice opportunity to report our recent research result on carbon-carbon fusion reaction for astrophysics. So let me start the presentation. So this work was made by collaboration with Professor Taniguchi at Kagawa College in Japan. Okay, so in this talk, I will discuss the relationship between monopole transition strength and astrophysical fusion reaction, such as carbon-12 plus carbon-12 or carbon-12 plus carbon-oxygen. And let me focus on carbon plus carbon fusion reaction because this reaction significantly impacts on the evolution of massive stars like this or X-ray superburst in a neutron star. And the conclusion of my talk is this. The monopole excitation of nucleus is a novel probe to identify this reaction rate. So this is the most important message from my talk. Okay, so let me explain this fusion reaction. This equation shows the main reaction channel. So we have a fusion of two carbon nucleus, and it goes to the compound nucleus of magnesium-24. And after that, it will emit proton and decays into sodium-23, or it can also emit alpha particle and goes to neon-20. And then typically, in the astrophysical environment, the reaction energy is around 1 to 3 MeV in the center of mass energy. And this energy corresponds to the excitation energy of magnesium-24, and that is approximately from 14 to 17 MeV. So this figure shows the reaction channel. So this is the incident channel, carbon plus carbon. And then after that, it decays to proton plus sodium-23 or alpha plus neon-20. And reaction Q values are shown in this figure. So you can see that this carbon-carbon reaction occurs at rather high excitation energy relative to the ground state of magnesium-24. So excitation energy of magnesium-24 is approximately 14 MeV or 15 MeV. Okay. And then because this reaction energy is very small, so there is very large Coulomb barrier for fusion reaction. And this makes it difficult to measure the reaction rate directly. So at the present, the direct measurements are limited down to 2.3 MeV in the center of mass energy like this. So this is experimental data. So horizontal axis is center of mass energy, and the vertical axis is so-called astrophysical S factor. This is something like reaction rate. And then measurement is up to 2.3 MeV. Therefore, but for the astrophysical simulation, we need low energy reaction rate. Therefore, people extrapolate this observed data to low energy based on some theories. And the most commonly used one is this one, the Kaplan-Fowler estimation by Kaplan and Fowler in 1988 that assumes the constant S factor at low energy. But recently, some people argue the hindrance reaction rate at low energy based on some observation in heavier mass nuclei. So this scenario is called a hindrance model. On the other hand, another people argue that the reaction rate might be enhanced at rather small energy. So in this way, there is no, no boundary condition from the nuclear theory or nuclear experiment. So people apply many different estimations of reaction rate. Therefore, we need the information from nuclear physics. And very recently, very important experiment was made by Catania group in Italy, and they used the Trojan horse method that is kind of indirect measurement of the reaction rate. And they proposed this solid blue line reaction rate based on their measurement. And you can see that very large enhancement at small energy. So this is very interesting. However, some people argue that the analysis of this reaction or this experiment is not sufficient or is not correct. And if you take care of the correction, some people argue that the reaction rate should be hindered than their estimate. So in this way, we have very large uncertainty in the reaction rate at very small energy. So this is the current situation. Yes, so this is the explanation. So this new experiment, Trojan horse method experiment, suggested many resonances at small excitation energy. As a result, the reaction rate was enhanced. And we know that if there is a cluster resonance like this, then the reaction rate is enhanced in order of magnitude. And also, the reaction product is determined by the decay process or decay pattern of this resonance. Therefore, identifying the cluster resonance at small energy is very important. So this is the goal of our study. So first, we will investigate the resonances at small energies by microscope. And also, because we only provide the theoretical result, so we propose an experimental method to confirm if our prediction is correct or not. So these 2 points are main topic in my talk. So let me skip the detail of the theory, but we use some nuclear model that is called unsymmetric molecular dynamics. That is kind of molecular dynamics in quantum chemistry. And we used this framework to investigate the reaction rate of carbon-carbon fusion reaction. So by using this, and this result is published in this paper. And by using this model, we have investigated the cluster resonances, the resonances in the energy region of astrophysical interest. And we also estimated the astrophysical S factor from our theory. So this red line shows our estimation, theoretical estimation. So let me explain how we obtained this estimation theoretically, and how you can identify or you can confirm this reaction rate by the experiment. So let me explain our theoretical frame which was used to estimate this reaction rate. So we use the full microscopic nuclear model, which treat each nucleon as independent particles. So our variational wave function is unsymmetrized product of nuclear wave packet. So that is symbolically described here. So this shows that our wave function is its letter determinant of nucleon wave packet. And each nucleon are described by Gaussian wave packet that is locally in the space and momentum space. And localization parameter is given by Z, that describes the position of the localization, and the width parameter of nu. So this nu describes the size of distribution of localization. And also each nucleon has spins. So spin is also parameterized in this way. That is rather standard way. And here, those red symbols are the parameter of our model. And these parameters are determined by energy variation. That is standard way. So let me confirm the meaning of these parameters. So first, the Gaussian center Z describes the mean position and the momentum of each nucleon. Therefore, by using some method, we can control the position and the momentum of each nucleon. Therefore, it is rather straightforward for us to describe all reaction channels, not only carbon plus carbon, but also alpha plus neon and proton plus sodium-23. Practical calculations, those parameters are determined by energy variation for each reaction channel. And this figure shows some examples of our wave function obtained by energy variation for each reaction channel with different internuclear distance. For example, upper panels shows the wave function for carbon-carbon reaction channel. So you can see that here there are two carbon-carbon nucleus in the left side and right side. And in this panel, the internuclear distance is 6.5 femtometer. So it is a little bit far away. And then it approaches to each other, and you can see that each nucleus, carbon nucleus, rotate because of the interaction between them. And then at a very short distance, they start to fusion reaction. And this is another example. This is the wave function for alpha plus neon channel at larger distance, 6.5 MeV. We can identify alpha particle here and also neon 20s here. But if we make the internuclear distance smaller, then you can see that each nucleus rotate, and then finally at a very short distance we have fusion. And the same reaction also occurs, proton plus sodium-23 reaction. So we can see here there is proton and we have sodium-23. But at short distance, it's absorbed into sodium-23 and make a compound state of magnesium. So by doing this kind of reaction, this calculation, we prepare many different configuration of carbon plus carbon, or alpha plus neon, or proton plus sodium wave functions. So we prepare the thousands of wave functions to calculate the reaction rate. Then once we prepare those different reaction channel wave function, okay. And then let me explain one of the advantages of this method. So in this method, we use the Gogni D1S finite length nuclear force density functional that is given here. And then the advantage of this Hamiltonian is that this Hamiltonian is very accurate to describe the energy of each subsystem. So this Hamiltonian can describe the binding energy of carbon and also neon, alpha particle, and also sodium-23. As a result, we can reproduce the reaction Q values, the binding energy of these nucleus, very accurately. So in this figure, we show the observed Q value and also our calculated Q value for these reaction channels. And you can see that, of course, our result is not perfect, but you can see very good, reasonable reproduction of the observed reaction Q values. This is one of the advantages of our method. And also, yes, so once we prepare many different wave functions in the reaction channel, we superpose all these wave functions and diagonalize Hamiltonian. So size of Hamiltonian is order of 10,000, and we diagonalize Hamiltonian and obtain the wave functions for the continuum and also resonances in the Gamow window. And finally, once we obtain the wave function for the resonances or continuum, we estimate the decay branching ratio by using R matrix theory. And in this theory, the partial decay widths of resonances are estimated by this formula. And here, PL describes the Coulomb penetration probability. As I already explained, there is a huge Coulomb barrier. So we should estimate the penetration probability. And this is very simple estimation of the penetration probability, which assumes the Coulomb interaction. So once we obtain the energy and reaction channel radius, we can easily estimate the penetration probability. And then we multiply the so-called reduced with amplitude. That is kind of spectroscopic factor for each channel. And this spectroscopic factor was calculated by some numerical technique that is explained in this paper. So I skip the detail, but by using this technique, we can accurately estimate the reduced with amplitude. So this figure shows some example of reduced with amplitude for this reaction. But anyway, once we obtain reduced with amplitude, then we can easily estimate, accurately estimate the decay widths of each resonance. As a result, we obtain the decay branching ratio. So the detail, the numerical result, I skip the detail, but obtained results are summarized here. And here, this column shows the calculated resonance energies. And you can see that there are so many resonances from 1 MeV to up to 4 MeV. Okay, so let me go back to previous slide. Yes, so you can see that this figure, you can understand that we are interested in the resonances in this energy region from 1 MeV to 4 MeV. And actually, by this calculation, we have obtained many resonances in this energy region by this model. And also, by using numerical technique I explained before, we also estimated the decay width and decay branching ratio that is tabulated in this table. So very important point is this. So by theoretical calculation, we have shown that there are some resonances at very small energies. Okay, so please let me go back to previous slide. So so this is the reaction rate as function of excitation energy, and then you can see some resonances in low energy region. So you can see some large peak in the observed data. And actually, our calculations suggest that there must be some resonances at small energy region. So this suggests that the reaction rate should be enhanced at small energies. So as far as we know, this may be the first result which showed the existence of resonances at small energies in carbon-carbon fusion reaction channel. And then by using these resonance parameters, I mean the energy of resonance and also decay branching ratio, we have estimated so-called astrophysical S factor to compare with some experimental data and also theoretical estimations. And this figure shows the result, and this red line shows our result. And you can see that this estimation is a little bit smaller than Kaplan-Fowler estimation, but much larger than this hindrance scenario at small energies. So this was our first result. And then let me discuss the more detail of this reaction rate. So in this study, we have used one of the standard density, nuclear density functional, or standard Hamiltonian for nuclear structure study. That is named Gognin D1S. But as you may know, there are many different set of Hamiltonian or parameter set for density functional. And we can imagine that each density functional should give different reaction rate. Therefore, we should have some uncertainty in the reaction rate depending on the density functional we use. Therefore, we have performed additional calculation by employing the different density functional, and we have estimated the reaction rate. So this figure shows how the carbon-carbon fusion reaction rate depends on the nuclear Hamiltonian. And in this figure, this horizontal line shows the standard estimation by Kaplan-Fowler made in 1988. So this is the most standard one used in the astrophysical simulation. On the other hand, the recent experimental data made by Catania group gives this reaction rate, the very enhanced reaction rate compared to the standard scenario. And also, this is another scenario proposed by astrophysical people. They also proposed a very enhanced reaction rate at small energy. And then this orange hatched region, this shows our result. So you see that some uncertainty at small energy region in our calculation, but uncertainty is not large in large energy region. But anyway, this uncertainty comes from the uncertainty of the nuclear Hamiltonian or nuclear density functional. So in this study, we have used many different density functionals, such as Gogni family or Scarm families. And then each of density functional gives us different reaction rate. And this hatched region shows the upper limit and lower limit of our prediction. So you can see that this hatched region is close to the Kaplan-Meier estimation, but some density functional gives us very enhanced reaction rate compared to the standard scenario. Therefore, we can say that this very simple estimation by Cooper is rather realistic. It has some reason. So in this way, we still have some uncertainty of the reaction rate from nuclear physics. So from now, let me discuss how we can reduce this uncertainty from the experimental information. One of the answers is isoscalar monopole or quadrupole transition measurement by the experiment. So let me explain our scenario. So our purpose is this. So our calculations show that there are some resonances within Gamow window, but we know that it is not easy to populate this resonance by this kind of fusion reaction because cross-section is super small due to the large Coulomb barrier. And instead of that, we propose to use isoscalar monopole or quadrupole excitation to populate this kind of reaction, this kind of cluster state. So I will show you that isoscalar monopole or quadrupole transition can populate this kind of resonances very strongly. And a very important point is that this reaction can bypass or skip this Coulomb barrier because we start from 24 and this state is transformed into this cluster state. And in this process, we have no Coulomb barrier. So this reaction cross-section, this cross-section is rather large. So you can measure it. So the key point is that this kind of isoscalar monopole transition from the ground state and excited cluster state is very enhanced. As a result, you can measure this cross-section. So let me explain why this transition is enhanced. And this mechanism was detailedly explained by Yamada-san and his collaborator in this paper. And I think Boston, the organizer of this seminar, is very familiar with this paper. But anyway, let me explain the mechanism of this excitation. For this purpose, let me start from Bayman-Boas theorem that is published in very old paper in 1950s or 1960s. And in this paper, we have proved a very simple shell model wave function is mathematically equivalent to a cluster, to a cluster wave function. So let me explain this theorem by using neon 20 as an example. And we all know that neon 20 wave function is something like this. We have oxygen 16 core plus 4 nucleons in the SD shell. So the wave function of neon 20 is given like this. And this theorem proved that this shell model wave function is equivalent to cluster wave function composed of alpha particle plus oxygen 16. So this is mathematically equivalent. So very roughly speaking, this theorem tells us that this kind of spherical shell model wave function is mathematically equivalent to the cluster model, cluster wave function, in which alpha cluster and oxygen 16 cluster are completely overlapped. So, so this is very important. So this theorem has very important message. So this means that even in pure shell model wave function, the cluster degrees of there is a degrees of freedom of cluster excitation. Let me explain this more detail. So this is this is a shell model wave function for neon 20. We have oxygen 16 core plus 4 nucleons in SD shell. And then let us consider the monopole excitation of this state. So monopole operator is given by this. This is the definition. So this is just the square of radius of each nucleon. Okay, and then you can imagine that you can apply this operator to the ground state wave function, and then remember that this is one particle, one operator. Therefore, by applying this operator to the ground state wave function, we can obtain one particle, one hole excited state. And then you can look at your textbook of nuclear physics. So the superposition of this kind of one particle, one hole state generate giant monopole resonance of nucleus. So this is a very standard understanding of monopole excitation of nucleus. Of course, this is true, but there is another scenario. So this is my point. So let me remind you that this shell model wave function is equivalent to the cluster wave function from the Bayman-Boas theorem. Okay, and then this is the standard definition of monopole operator. And here I make the linear transformation of the single particle coordinate. So this is a standard single particle coordinate, but I make the linear transformation to the cluster coordinate. And here cluster coordinate is composed of coordinate R and coordinate Z. And here Z is internal coordinate of each cluster, I mean oxygen 16 and alpha particle. And also R describes the intercluster coordinate. And this is just a very simple linear transformation. And by doing this very simple transformation, this monopole operator can be written in this way. This is a very simple transformation. So this is a very good homework for the student. But anyway, here, the last term depends on the R square. And here, R is intercluster motion. So motion of relative motion between oxygen and alpha cluster. And now you can imagine that if you multiply this operator to this neon 20 wave function, this last term excites the intercluster motion between alpha particle and oxygen cluster. As a result, we can naturally conclude that if you operate this isoscalar monopole operator to the shell model ground state, then the distance between alpha and oxygen cluster becomes large, very naturally. As a result, by the monopole excitation, we can obtain cluster state. And remember that for this argument, I haven't used any detailed properties of Hamiltonian. Okay, I just use very simple mathematical equivalence, Weber-Boer theorem, and also I only use linear transformation. So this is very trivial result, model independent, simple result. Therefore, we can say that this monopole excitation can populate cluster resonance in a very model independent way. This discussion is not dependent on the detail of each nuclear model. So this is very global conclusion. And I skipped the detail, but we can say we can make a very similar discussion for the dipole excitation and also quadrupole excitation. And we can easily calculate this transition strength is very large by some analytic calculation. And reference is given here. But anyway, very important point is that we can say that the cluster structure should be populated by monopole or quadrupole or dipole excitation very strongly. And this argument is independent of nuclear model. So now we can understand why in the experiment, we often observe this kind of strength function. So if you look at the experimental data, we often observe very large strengths in highly excited region. That is called giant resonance. But if you look at very small energy region, we can observe many strong discrete resonances. And those resonances, some of those resonances must be cluster state because those cluster states should appear close to the decay threshold energy that appears at small energies. Okay. Therefore, by measuring this kind of isoscalar monopole or quadrupole transition strengths, you may be able to identify the low-lying cluster state very close to the Gamow window that is important for the astrophysical reaction. So let me introduce some experimental data from Texas A&M University, measured in 2009 or 10 or in these years. So this is experimental data for magnesium-24, isoscalar monopole dipole strength, and also silicon-28. And here, histograms show the observed data. On the other hand, the solid line shows some RPA calculation which describes giant resonances. And you can see that there are so many sharp resonances are observed at small energies. And those resonances are not reproduced by RPA calculation. I mean, those resonances are not explained by giant resonances. And I believe that some of those resonances must be cluster resonances. And let me remind you that you can see some resonances in the region of 12 or 15 MeV in magnesium-24, here and there. And this energy just corresponds to the Gamow window of the carbon-carbon fusion reaction rate. Therefore, I believe that those resonances should have some impact on the carbon-carbon fusion. So let me introduce our numerical results. So let me skip silicon-28. Okay. So this is our result for carbon-carbon, I mean magnesium-24 system. And we also calculated isoscalar monopole and isoscalar quadrupole strengths. And you can see that this strength is rather strong, very strong. Therefore, I believe that those observed resonances should correspond to our numerical result. And then, okay. And then recently, there is some experimental data from Itemba laboratory in South Africa, and also data from Osaka universities. They observed some resonances at small energy, 14 to 16 MeV. And here, this hatched region corresponds to the Gamow window for the astrophysical reaction. So you can see that actually there are some resonances as we predicted. Yeah, and I couldn't include into my presentation, but very recently, maybe last month, the new data was published from Itemba laboratory, which was published in Physical Review Letters, and they finally reported that there are some resonances, 0+ resonances in this energy region. I'm sorry, I haven't included those latest data in my presentation, but anyway, now some people are searching for the resonances in this energy region by this alpha prime reaction. So let me summarize my presentation. So I have focused on the monopolar transition and carbon-carbon fusion reaction. And we have shown by the microscopic calculation that there are some resonances which enhances the reaction rate in the Gamow window. And we propose to use the monopole or the quadrupole transition to identify these resonances. For this purpose, you should perform this reaction, magnesium-24 and alpha prime reaction. So by doing this, I believe that you can identify the cluster resonances in this very low energy region. So this is the conclusion. So thank you very much for your attention.
Thank you. Yeah, thanks, Kimura-san. Very nice talk. So next is a question time. So if you have some questions, please raise your hand in Zoom. Maybe first I want to ask some questions. First is about the in your slide you mentioned you reproduce the very exactly the Q values, different channels.
Yes.
Yes. Here. This how to reproduce this exactly? I mean, you don't have any adjust parameter or something, because this Q value is very important to calculate the part of the leaders. So here I want to know, exactly.
Yeah. So this Gogni DIS functional is very nicely designed or parameterized to reproduce the binding energy of a stable nucleus. And to reproduce the Q value, okay. So first, let me explain that to reproduce the Q values, we need to reproduce the binding energy of each nucleus, such as carbon, neon, alpha particle, and also sodium-23. And then this Gogni DIS functional is very accurate, very nice one, I believe, because this functional can reproduce the binding energy of carbon, neon, alpha, and sodium. As a result, we can reproduce those Q values pretty accurately.
Okay. So next
that is
is
already designed, nicely designed.
So in your calculation, you get several random states. I mean, the very low-lying states. And in the end of your talk, you mentioned some experiment data. I want to know, in your calculation, is there some new state? I mean, without experiment information? Yes, here. This is there some experiment information for this low line, or there are some new states in your calculation?
Okay, so let me explain the situation. So there was no experimental data as shown here for the resonances in very low energy region. Okay.
Very low. Okay.
But there is indirect measurement by Torre-and-Horst method, and that proposes the existence of many resonances. But they cannot give us spin parity of those resonances.
Okay.
And also, we don't know this, and also I personally don't know if those data are correct or not. This is the situation.
Yeah.
But very recently, very recently, Itemba group observed 0+ resonances by alpha prime reaction, and I'm sorry, I forget their result, but I believe that I remember that they observed at least 2 resonances in the Gamow window, whereas we predict one resonance in Gamow window. So agreement is not perfect at the moment, unfortunately. And I think the Sheldon has some question. Thank you very much.
Yes. Please tell us.
Kimura-san, can you hear me?
Yes.
Well, thank you again for this very nice talk. I learned more about the theory. So I have regarding to this recent result from Phil Addersley, the PRL papers. They only report 2 0+ strong resonance.
Yes.
In their paper.
Yes.
At around 1.5 MeV.
Yes.
Yeah. So, but here you predict the 2+ states.
Yes.
Yeah. So now come to my. Can you go to this error bar plot? You use different interactions.
Okay. Yes.
This plot.
One? Yeah.
Yes. I think here you might overestimate the uncertainty from your calculation. The reason is that different interaction will give you different kind of a resonance energy.
Yes.
And then when you apply this so-called if you translate this theoretical reduced width to this observed width, they are sensitive to energy.
Yes.
So maybe here, I suggest if you can like follow same kind of structures, but using different interactions. So they will have a probably different kind of a reduced width, but try to find some way to align them to some kind of energy, and then you can reduce the dependence on this penetration factor effect.
Yeah.
So
maybe I think I understood your intent. So let me explain. So
yeah, please.
Yes. So we used many different density functional in this calculation. Okay. And then in all cases we obtain 0+ state. but the energy of zero plus state is dependent on density functional. And we are not sure which one is correct, but now we have experimental data from ASLI, from iTember, so we can calibrate the excitation energy by adjusting our result to the observation. By doing that, we can reduce the uncertainty of the Q value from our calculation. Is this your intent?
In principle, you're right, except you don't really know from the experimental side which resonance corresponding to your resonance. So this kind of one-to-one correspondence is a little arbitrary, but at least for your theory side, you can choose one as a standard, and then you align the others with this standard one.
I understand. So
this will be biased, but eventually when you find another way to link the experimental results with this kind of a nominum model, and then you will finish the whole path.
Okay, thank you very much. Very nice suggestion.
Yeah.
Please.
Oh, I wanted to ask another one.
Yes.
So in your model calculation, do you have something like a cutoff radius? If you do, how will you deal with this long-range Coulomb interaction?
Okay, so at the cutoff, the wave function, our wave function is connected to the Coulomb wave function.
I see.
So in other words, the cutoff radius is determined so that our wave function is smoothly connected to the Coulomb wave function, Coulomb scattering wave function.
I see. Okay, thank you.
Okay, so please, Biden, please.
Kimura-san, can you hear me?
Yes.
Okay, thank you very much for a nice talk. I have two technical questions. The first is, how do you choose the channel radius in your calculation when you calculate?
Okay. Can I answer to your question for your first question?
Yes, please.
Okay. So that is not shown in this figure, but here I showed, for example, this is the wave function from alpha plus neon, this oscillate. And then because we are solving the problem in the finite spatial size, therefore this is not accurate. In reality, the scattering wave function should have infinite radius. Therefore, we find the channel radius where our wave function is smoothly connected to the exact Coulomb wave function, Coulomb scattering wave function.
Okay.
It's okay?
Okay.
Yeah.
Okay,
so
thank you.
We already know the behavior at large distance that is given by Coulomb wave function. Therefore, we smoothly connect our wave function to the Coulomb wave function at some distance. That condition gives us the channel radius.
Okay, thank you. My second question is, as you mentioned in your talk, you use 10,000 bases to do the calculation. How to choose 10,000 bases in your calculations?
Okay. I'm sorry, I skipped the detail. I'm sorry. Okay, so let me explain what we did. So first, we calculate the wave function for each channels, carbon plus carbon, alpha plus neon, proton plus neon, and also all other opening channels. And then basically, we obtain these wave function by energy minimization or energy variation. But in this energy variation, we fix the distance between two nucleus. So in this, for example, in this calculation, we fix the distance between carbon plus carbon, carbon and carbon at 6.5 meter. And we minimize the energy and we obtain this wave function. But if we apply smaller distance, we obtain this different wave function. And we do the same thing for different reaction channels. And by continuing this calculation, we obtain the 10,000 wave function. Is this your answer? It's okay?
Yes. So does your calculation converge? So when you add, for example, another 100 bases,
yes.
Calculation...
That was also confirmed. In practically, we applied different set of different number of wave function, and we confirmed the convergence of our result.
Okay, thank you very much.
Yeah.
Okay, so Zhao Jin, please.
Thank you very much, Kimura-san. Here is Qing Zhao from Fuzhou University.
Yeah.
And my question is that you prepare the carbon plus carbon wave function for your calculation. So my question is, what's the difference with your carbon plus carbon wave function and, for example, the magnesium 24?
Okay, it has some overlap. Okay, I haven't explained the wave function for magnesium 24, but in magnesium 24 wave function, we don't have this kind of very clear cluster structure.
Yes. So my question is, what's the different treatment for the carbon plus carbon wave function?
Okay, so when we calculate this carbon-carbon wave function, we put the constraint on the distance between two nucleus, carbon plus carbon, or alpha plus neon. But when we calculate magnesium 24, we don't put any such constraint.
Okay. So do you treat how simple? Do you trace the diagonalization for the for each nucleus?
Yes, everything is superposed and diagonalized, as you know.
Yeah, diagonalized. Okay, I understand. Thank you very much.
For this wave function, you use deformed waders here. That I think if you compare the RWA, there are some difference, right? So
sorry, Bosan, I couldn't understand your question.
In the model in AMD, yes, on this slide, you are using the deformed waders.
Okay.
Here.
Yes.
So that if you calculate the RWA, I'm thinking if you are using the same waders, there could be some difference, right? Because this in Chiba-san paper, he shows some difference using these waders. So if we use, for example, because most people are using the same waders, I think they not deformed, spherical. In that case,
Bosan, I think you are talking about not radius, but Gaussian parameter.
Waders. Yeah, Gaussian waders.
Gaussian parameter.
Yes, right. Yes.
Not spherical, but deformed Gaussian. Yeah. Okay.
Yeah, you are using deformed. So then after superpose the many configurations, you show us the RWA. And I remember in Chiba-san paper, he compared the spherical one because many people are using the spherical one, and there's some difference. So, so how much this difference can give the final difference result. I want to know some system for this kind of wave function, the inference or the final reaction rate.
Okay. So we haven't tested spherical Gaussian for this calculation. But I can say there may be some differences. But most important point is that if you use spherical Gaussian, then I can tell you that you cannot reproduce Q value.
Okay.
To reproduce this Q value correctly, then use of deformed Gaussian is essential.
Okay, thank you. Yes, that's what I want to know. Okay. Maybe next is John Nicholas, please.
Okay, yeah, hi Kimura-san, I'm Ningtao from IMP. So yeah, thank you a lot for your nice review. So I have a question for your calculations. Your results, the average results seems a little bit lower than the experimental data. So could you explain it? So
you mean this result?
Yeah, compared to the experimental data, your calculation.
Yes, that is problem we have at the present, and one of the reasons of this may be due to the some small difference in Q value. That is one thing. The another thing is that the number of resonance we obtained may be smaller than that observed in the experiment. And this may be due to the smallness of our model space. I mean, we only included carbon plus carbon and alpha plus neon and proton plus sodium channels. And there are some channels which are not included in our calculation. So we should enlarge our model space to cover a more physical situation. And such kind of calculation is now undergoing. Yes, I agree with you. Our calculation is not perfect.
Okay. Yeah, for the opening channels, some people claim the beryllium-8 emission maybe also play an important role in the fusion cross sections. So
Yes. Thank you very much. Yes. So we are now trying to include beryllium-8 plus oxygen channel. Indeed. Thank you very much.
Yeah. Okay. Thank you. Yeah.
Please.
No, Zaifon.
Yeah. Please.
Hey, hello, Kimura-san.
Yes.
So, yeah, thanks for your nice talk. I have a question related to your formula connecting the reduced width amplitude and the partial decay width. So, there it seems you simply multiply for each channel, for each decay channel, you multiply this penetrability to the reduced width amplitude, and then you obtain the partial width for each channel, right? Yeah, so maybe my level question is, now you have different decay channels, so kind of you have your wave function for this state is a combination of different components. Then still now we can use this simple formula to, this penetrability.
Yeah, thank you very much. Very nice question. Yes, this is just approximation. So we are now trying to improve this treatment. Yes, as you mentioned, when we have many, when we have many different decay channels, then this is not a good approximation, I believe. So now I and Taniguchi-san is trying to connect our wave function directly to the decay channel. So in the future, we will not use this formula, but we directly calculate the decay width from our wave function. Yeah, this is just a R matrix approximation.
Yeah.
Yes. And
Okay,
this is not perfect.
Okay, so any questions? Yeah, please.
Yeah, may I ask what is the branching ratio for carbon-carbon to alpha plus neon 20 in your AMD calculation?
I'm sorry. Okay, it depends on the energy, of course, which is the energy. And I'm sorry, I haven't prepared the slide and I haven't prepared the figure.
So is it the dominant channel for carbon plus carbon to alpha plus neon 20? Is this channel dominant one?
If I believe correctly, both are comparable in general.
Comparable?
Maybe.
Okay.
I'm sorry, but in the next paper, in our paper, I will show, we will show the result. And it depends on the energy. Okay, Sheldon has more accurate answer to your question, I believe.
All right. Okay. Thank you.
Please. Yes.
Well, for this branch ratio, we only have a experimental analysis. So I have a comment on this Lin Tao's questions. Can you go back to that figure? You compare your theory.
This one?
Yep. So so in this calculation, you only consider the resonance at a low energy. Actually, they have many resonance at a high energy and also have this giant resonance, whatevers. All of them can extend their tails towards this region and form certain like a background. So all this resonance you predicted should on the top of this background. Okay. Yeah. So you also need to consider this high energy contributions.
Thank you very much.
Yeah.
Okay, so any questions? Okay, I think it's almost time. So thanks again for Kimura-san's very nice talk.
Thank you very much.
So yeah, could you send me your slides? I think
of course,
some people are very interested in you.
Yeah.
Okay. Okay, so then see you next time. Okay, bye.
Yeah, see you next week. Thank you very much. And I hope you invite me to Shanghai near future.
Yeah, of course. No problem.
Anywhere you want.
Yes, right.
Okay, so goodbye.